When you think of an iron foundry, it's easy to picture this old-school industrial revolution scene, right? All fire and sweat and just brute force. But the reality is, a modern foundry is so much more than that. It's less of a furnace and more like a high-tech lab, a thermochemical system where some serious science dictates every single thing that happens.
So what if you could actually do that? What if, instead of just pouring this glowing liquid metal and kind of crossing your fingers, you could literally ask it what it's doing, what it's thinking, as it goes from a liquid to a solid? That's really the big idea we're going to get into today. How we're finally getting a clear view into a process that's been a mystery for centuries.
All right, let's get right into it. The melting furnace. It's not just a simple pot where you melt stuff down. It's this incredibly dynamic, almost chaotic place. The tiniest little changes, things you can't even see, like a slight shift in temperature or chemistry, can have huge, and I mean huge, consequences down the line.
And this right here, this is what happens when that chaos wins. What you're looking at is a nasty defect called microporosity. These are tiny little voids, totally invisible to the naked eye, but they can completely wreck the strength of a critical part. This means scrap, waste, and sometimes failure. It's really the price you pay for not knowing what's going on inside that molten metal.
So, where does all this unpredictability even come from? Well, it's everywhere. How hot you get the metal, how long it just sits there, how fast it cools, even the tiny trace elements in the scrap metal you use. Then you've got your alloy additions, and even just the temperature of the ladle you're pouring into. Every single one of these is a variable that can throw the whole process off. But here's the cool part. Here's how we fight back against all that chaos. Foundries have this amazing tool that basically gives them a window right into the molten metal. It's called thermal analysis, and it lets us read the unique fingerprint of every single batch of iron as it turns from a liquid to a solid.
To put it simply, thermal analysis, or TA, is like running an EKG on molten metal. You just take a tiny sample, you let it cool down naturally, and you record its temperature over time. That super simple curve it creates, it's packed with a ton of information about what's happening deep inside the metal as it solidifies.
And this is what that fingerprint looks like. This is a cooling curve. Now I know, it just looks like a line going down, but trust me, every single plateau, every change in slope, every dip and rise, it's telling a detailed story. It's the secret language of the melt, showing us its journey from a chaotic liquid into an ordered solid.
So let's break down the key parts of the story. First up, you have the liquidus temperature, or TL. That's the exact moment the liquid starts to freeze. Then you get this super important dip, called eutectic undercooling. You can think of it as the metal kind of struggling to solidify, and a big dip is a bad sign. And finally, you get this thing called eutectic recalescence, which is this cool rebound in temperature when the bulk of the metal finally crystallizes and releases a burst of heat.
Okay, that undercooling dip is the real hero here. If that dip is really deep, that's high undercooling. It's a huge red flag. It's telling you the solid structure isn't forming easily, and you're probably going to get brittle spots and defects. But a shallow dip, low undercooling, tells you that conditions are just right for a strong, solid casting. It's a direct prediction of the final quality. But see, this isn't just about predicting if something will fail, it's about actively stopping it from happening in the first place. So let's look at how this data lets us do some real-time engineering, starting with adjusting the metal's chemistry on the fly.
One of the most critical numbers in cast iron is something called the carbon equivalent, or CEQ for short. It's basically a single value, calculated from the carbon and silicon in the mix, that tells you a whole lot about the final properties of the iron. And believe me, getting this number right is absolutely crucial.
And here's where the magic happens. That very first point on our cooling curve, the liquidus temperature, is directly linked to the carbon equivalent. So by just measuring that one temperature point, a system can calculate the CEQ with incredible precision, not in hours from some remote lab, but right there on the foundry floor in just a couple of minutes. So picture this. The analysis pops up and says your carbon equivalent is, say, 0.14 units too low. Instead of just guessing, the system can calculate the exact amount of carbon or ferrosilicon you need to add to that ladle to bring the metal perfectly into spec. You do this before a single casting is even poured. Now that's engineering, not guesswork. But just controlling the chemistry, that's really only half the battle. The real art, the real science, is in controlling the microscopic structure of the iron itself. We're talking specifically about how the graphite forms inside it. It's all about mastering something called nucleation. This quote really hits the nail on the head. You can't just expect the right structure to form on its own. You have to actively build it, you have to engineer it. Making a high-quality iron casting is a totally intentional, precision-driven process.
And the main tool we use for that engineering is called inoculation. Now, this isn't about just changing the chemistry. It's about adding a tiny amount of a very specific alloy that acts like seeds in the molten metal. These seeds give the good graphite particles a perfect place to start forming and growing.
And wow, the results are just night and day. On the left, you've got an undertreated iron. See how the graphite is all sparse and weirdly shaped? But on the right, after proper inoculation, you get this dense field of perfect, round little graphite nodules. That is the microscopic signature of a strong, reliable part, and it was created completely on purpose.
So what happens when you take all this deep scientific understanding and you combine it with modern automation? Well, you get the smart foundry of the future. You literally transform the whole process from a mysterious black box into a predictable, digitally controlled system. The shift in thinking here is massive. For centuries, casting was a reactive game. You'd make a bad part, find the defect, and then try to figure out what went wrong. With thermal analysis, it becomes predictive. You can see the potential for a defect forming while the metal is still liquid, and you step in to prevent it from ever happening. And it all comes together in this awesome automated system called the feed-forward control loop. The system measures the melt, it analyzes that unique fingerprint, it calculates the exact additions needed, and then it automatically adds them to the ladle. What you get is an incredibly controlled, super repeatable process that delivers quality every single time. You get to cast with total data-backed confidence.
Which kind of leaves us with a big question, doesn't it? Thermal analysis is basically letting us listen to the heartbeat of solidifying metal. So if we can bring this level of insight and intelligent control to a process as ancient and fiery as casting, what else is possible? What's next for the future of manufacturing?